Welcome back, and let us start with our resume of the discussion on noise, and we will be looking at the differential amplifier circuit with active load that is being used for building our op amp, and then we will be looking at some of the sizing issues related to reduction of this corner frequency 1 upon SC, and also look into some other techniques that can be used to mitigate this 1 upon FC noise, which also involves trade-offs with some other design matrices. So, let us look at these topics one by one. So, if we look at the differential amplifier operation, we will be looking at the differential half circuit, and then we can say that ultimately our differential half circuit is going to be same as what we have just analyzed, active load circuit. If we however look at the common mode, we have just got to take care of another transistor which is at the tail current source. So, you have M1, M2, M3, M4. For the differential case, we do not have to worry about the tail current source. We said this is AC ground. So, anyway we do not have contribution coming from this one. For the common mode also, if you look at the two paths, you have some equivalent noise voltage and current because of this transistor, and this is going to result in an overall equivalent noise current flowing through the drain of this M5 for the common mode. Therefore, this is the same source which is contributing to the VON1 and VON2. So, if I consider effect of only M5, its effect appears like a common mode because it is a single source. So, its effect is getting divided, and you are having an overall noise current flowing in these two branches and coming at the output nodes over here, and these are correlated because they are coming from the same source. So, you can have an overall noise coming in the common mode operation because of this transistor, and we are not concerned with the common mode signal so much. So, an overall common node noise which is much minute as compared to the signal can be relatively less significant as compared to the differential operation where it is not appearing. So, this is just a small point to be noted over here. Now, if we look at say the minimization of FC, if we revert back to our expression and try to see what it takes to minimize FC in order to cater to our low frequency signal. Remember, we are talking about signal content which is going all the way to 0.5 hertz, and we need to pass up to 0.5 hertz of signal, and our higher cutoff frequency for the high pass response also that we designed with the help of that feedback resistor RF for input DC biasing, that was also supposed to pass that 0.5 hertz. So, we need to ideally shift FC to 0.5 hertz if we rely only on sizing, and once again referring back to our discussion earlier, if we look at the 1 upon F frequency that will be obtained by the ratio of these two terms. So, we just equate this and get the F at which these two are equal, and that again mandates much larger L2 value, that would mandate a large ID value because in this ratio ID will be coming in the denominator term, and that will once again mandate a larger ID value, and along with that also a larger W by L1 value. So, these are the three terms we will like to increase: ID, W of the input device, that is making it larger size, and likewise making the channel length of the output device or the load device much larger. These are the three quantities that we figured out in order to push this 1 upon F frequency towards lower and lower values. So, we see the trade off with the bias current first of all, and in our case when we are having a low power application, we are talking about multiple channels, each of them having such a dedicated front end amplifier. Bias current is having severe constraint, and therefore, we cannot just go on reducing we just cannot go on increasing the bias current to cater to 1 upon F noise requirement. Likewise, the other terms, if you go on increasing W1 or the device size L2, they are going to affect my bandwidth because they are going to increase the device parasitic capacitances and slow down my overall frequency response, and we need to cater to up to at least 100 or 1 kilohertz of signal. So, being conservative, we would like to push the upper cutoff frequency slightly higher than the signal content. So, signal content is from 0.1 to 100 hertz. We would like the upper cutoff frequency to be at least a few hundreds of hertz to kilohertz, and we must meet all those constraints while we are sizing these input devices and the channel length of the load device larger. So, if we just rely on those two considerations, we will definitely have conflict with our bandwidth requirement, will also have conflict with our power budget that we are having for the overall amplifier. So, we need to look into some other techniques through which we can possibly have a better solution for this 1 upon f noise. And before we go there, we can also once again quickly revisit the second stage and just conclude that its noise, it's not so very relevant as compared to the first stage. Therefore, we are focusing more on the first stage noise, and without doing much of an analysis, we know that the whatever noise is produced by the second stage, I can call it VON2 square over here. Ultimately, magnitude point of view, they are going to be same because they are symmetric devices. So, the mean square value is supposed to be same, and if we want to refer it to the input, it gets divided by the first stage gain as well as second stage gain. So, VON square, if you want to find its equivalent input referred noise, that gets divided by GM_RO by 2 whole square. As a result, its contribution will be much lower as compared to the noise produced by the first stage. So, we are concerned with minimizing the noise contributed by the first stage, and we should just make sure that under no condition the second stage noise is degrading too much. That will not happen generally because of other design constraints. We are having the W by L and the bias current in the second stage also comparable to the first stage. So, we can try to save some power dissipation by allowing lower bias current in the second stage because it is not so noise critical. So, we can certainly take the advantage of this relaxation in achieving some advantage in the second stage by having more relaxed constraint on W by L and bias current. So, we are mostly focusing on the first stage for this determination of 1 upon f noise or minimization of the 1 upon f noise through the technique which we are going to discuss next. So, the technique that is commonly used for mitigating the effect of this 1 upon f noise is chopper stabilization, where we have an input signal which may be lying at very low frequencies. So, for example, in our case, as we have said, the content of the signal may be peaking at close to few tens of hertz, and it can have content going all the way to 0.5 hertz. So, it can be having some content very close to DC also. And therefore, if I look at the complex frequency spectrum, it will look like this. You have the positive and the negative frequency component in the complex frequency domain coming in, and so this is the overall signal spectrum centered around omega equal to 0. And I, under this condition, I also have at present the 1 upon f noise, which is which can be very sharply overlapping with this, even if you are designing it very carefully, trying to push 1 upon f noise further and further. We said that up to 10 hertz it may be feasible, but beyond that it becomes difficult. So, definitely we would like to save our signals from this increasing 1 upon f noise, which can significantly corrupt or completely destroy our signal content, at least those which is closer to lower frequency, closer to DC. And to do that, the technique uses chopping, where we multiply the input signal coming to the amplifier with a high frequency clock signal. So, schematically you can represent it as a multiplication operation, where you are having the input signal getting multiplied by plus minus 1, and as a result, the overall frequency spectrum of the input signal will be getting shifted by the frequency harmonics of the square pulse. So, we know that the square pulse is going to have harmonics at the fundamental frequency of this square and also the higher harmonics. So, I can represent this as A1 cos omega 1 t plus A2 cos omega 2 omega 1 t and so on. And omega t and so on. So, we can expand it in the form of its Fourier series, and we can look at the coefficients, and when we multiply this entire quantity by the input signal, call it V I N t, which is having some spectrum. So, this entire frequency spectrum of V I N t will be shifted to these higher harmonics and the fundamental harmonics of the square pulse. So, if I assume that this V N t is having some frequency content. All these frequency content ranging from say 0 to a certain frequency, call it omega bandwidth, will be shifted to this omega 1 and the higher harmonics of that, and therefore, I can represent my shifted signals as the magnitudes will be reduced as because the coefficients of the expansion will be diminishing as we go towards higher frequencies. So, let me draw it a little bit. Let me this is supposed to be let me draw it afresh. So, I just drew it equal magnitude. So, the shifted ones should be having lower magnitude. So, you had the original signal over here. So, signal shifted to f1, f2 having further lower magnitude and so on. So, this is the spectrum we are going to get after the multiplication of the signal with the square pulse, and then after the amplifier we can once again go back with the reverse process. We can once again multiply it by the same frequency, and if the amplifier is having its bandwidth which is limited, it will definitely reject the higher frequencies harmonics coming into picture. We know that ultimately our amplifier is going to have some band limitation, and we make sure that it is sufficiently lower than f2. So, we can ignore the higher harmonics coming into picture and assume that they will be diminished. We can also have a dedicated low pass filter which is anyway going to suppress this. So, in order to completely eliminate this, in some cases people may put a dedicated low pass filter stage. If the cutoff provided by this amplifier is not sufficiently low, or it is not guaranteed to be low and sharp enough, we can also incorporate a low pass filter over here before we go for the anti chopping process. So, at this stage basically what we are expecting is we are left with only the f1 component, the component of the signal shifted to f1 frequency, and also we have at this point the 1 upon f noise still sitting at the low value. So, I am drawing the signal Vx over here. So, this is let me call it Vx. The node Vx is having the 1 upon f noise spectrum still over here, because just at the output of the amplifier the 1 upon f noise spectrum will be as given by the original amplifier. However, the signal has been shifted towards higher frequency because of multiplication with f1, and the higher harmonics have been rejected because of the low pass filter characteristics of the amplifier or presence of a dedicated low pass filter just after the amplifier. And now, once again if I multiply this signal back with the same frequency, once again you will have this entire spectrum of the signal sitting at f1 shifting back to the lower frequency or the omega equal to 0 frequency. So, once again if I multiply this with the square pulse, the final signal that we get over here is once again going to come back to omega equal to 0, because the signal centered around omega 1 multiplied by cos omega 1 t once again is going to result in the DC component, and signals in the vicinity of omega 1 accordingly get shifted towards the frequencies in the vicinity of omega equal to 0. So, we get back our desired signal. However, if I talk about the 1 upon f noise spectrum, what happens to that after the point, let me call this Vy. So, what happens to the 1 upon f noise spectrum at Vy? So, before the anti chopping switch, this is called anti chopping switch, this is the chopping switch. So, here we did the chopping, we multiplied this frequency with this chopper which is plus minus operation, and after that we are having the anti chopping where we are again multiply the signal with the same frequency and shifting the signal back to the original spectrum. And if I look at the 1 upon f noise spectrum, however, that was sitting over here at the base band or low frequency, it was going much sharp, going much higher at lower frequencies, but now I have basically shifted this 1 upon f noise to f1 after the anti chopping operation, because for the 1 upon f noise over here this is acting like the chopping operation. Therefore, this gets shifted to f1, and my desired signal is back at lower frequency. So, basically I have been able to separate out my 1 upon f noise component with the desired frequency component, and hence mitigate the effect of this sharply increasing 1 upon f noise component at the low frequency, which was interfering with my data. Now, if I assume that the signal has been sufficiently magnified, so you also have this magnitude which is a times the input magnitude, which is going to be significantly higher, and therefore the 1 upon f noise or the thermal noise of the subsequent stages may not be so significant as compared to the signal over here. So, this is one of the ways in which we can mitigate the effect of 1 upon f noise. Now, if you look at this is the ideal picture. There are of course some issues related with this 1 upon f noise cancellation and chopping as well, and that is going to help us in determining how to choose these frequencies, the chopping frequencies, and what are the trade-offs in choosing the chopping frequencies appropriately. So, let us first look at the choice of chopping frequency. What should be the chopping frequency? So, one of the criteria that we always have is this 1 upon f noise corner, and we would like our signal to be sufficiently higher than this 1 upon f noise corner, so that it is not affecting our signal. So, definitely the obvious answer at the first hand will be that it should be sufficiently higher than this corner frequency, so that after the anti-chopping process the signal is sufficiently higher than this 1 upon f noise, and again when I am turning it back, it is the desired signal is coming back, and the 1 upon f noise spectrum is shifted to a much higher frequency given by the chopping frequency f1. So, in general the choice of f1 is at least 3 to 4 times this corner frequency. So, if your corner frequency is 10 hertz, I would like to keep this f1 at least 4 or 5 times that the corner frequency. So, a safer limit is 10 times, so that you can have an order of magnitude difference between the corner frequency and the center frequency of the shifted signal, and of course, it depends upon the bandwidth also. So, here we are assuming is that the bandwidth of the signal is sufficiently lower than f1. If it is comparable, then once again you will have to take the limit on the lower side and say that this f1 minus the bandwidth of the signal should be sufficiently higher than the corner frequency. But if I assume that the f1 is sufficiently higher than the signal bandwidth, then we can ignore this bandwidth as compared to f1 and just make sure that f1 is sufficiently higher than the corner frequency. Also, ideally, since this is a 1 upon f noise curve, so here we are depicting it with a very sharp characteristics that there is a transition, sharp transition between the 1 upon f curve and the white curve. So, we are depicting it something like this, but in the actual scenario, of course, this is a 1 upon f curve which is going to have smooth decay, and then you have the white noise which is flat overall. So, if we go higher and higher towards for the chopping frequency, definitely the effect of this 1 upon f noise will become will be diminished more stronger. So, crudely we can say that 1 upon f noise corner frequency is the deciding point. If we make sure that the f1 to which we are shifting the spectrum is sufficiently higher as compared to the 1 upon f corner, it seems like we can get a sufficiently good input referred noise, we are able to mitigate this 1 upon f noise. But if you are more greedy, we want to be even better in terms of the 1 upon f noise or overall input referred noise, we would like to push the signal as far as possible, so that even the tail effect of this 1 upon f noise is not coming up and it is not affecting the signal. Because remember, when you are talking about high precision signal, when you are talking about 10 bit, 11 bit, further higher 16 bit of precision, even this tail effect of noise which is increasing your overall noise can be important to address, and we would not like to have even this tail effect corrupting our signal. So, we would like to take maximum possible advantage of the chopping and try to shift the signal frequency even higher by applying a much higher chopper frequency, so that my signal after chopping is sitting far away from this 1 upon f corner, and also by that chopping frequency f1, the tail effect of this 1 upon f frequency has also diminished significantly. Or in other words, suppose the white noise level is given by V N W. If this 1 upon f spectrum has fallen 1 upon 10 times of that till this point, we would be having a safer limit. We would say that the contribution of this 1 upon f noise is now 10 times lower than the white noise, therefore, it is not very significant now. So, if you want to be more aggressive and save as much signal integrity as possible, you would like to push this 1 upon you would like to push this chopper frequency as high as possible, so that this trailing part of the 1 upon f noise is also not having significant effect. So, analytically it can be shown that the overall contribution of the 1 upon f noise is significantly lowered if the f1 is an order of magnitude higher than the corner frequency. So, if you make f1 approximately 10 times of the fc, the contribution of this tail of 1 upon f noise spectrum is falls significantly lower than the white noise, and then you are having a maximum or the signal to noise ratio almost saturating. So, if I plot the signal to noise ratio versus frequency, it will go on improving till this point. So, if I plot the SNR, it will be very bad in the initial phase, and after that it will go on improving, and after a certain point it will saturate. So, I would like to go to that saturation point. Beyond that, if you increase the chopping frequency further and further, because this has anyway died down, the tail of this 1 upon f has anyway died down, it will not have significant advantage. So, if I want to increase this further, I am not going to get significant advantage in the SNR of the circuit, and therefore, I would like to stop over there. Why I would like to stop over there? Because once again, what does a larger chopping frequency require? So, if I am trying to impose larger and larger chopping frequency to push my signal spectrum much away from this 1 upon f and much further away from the tail of this 1 upon f, I am enforcing larger clock frequency on these two multipliers, and along with that I am also having a constraint on the bandwidth of this amplifier, because in absence of the chopper, the bandwidth of the amplifier was just supposed to cater to the input signal, but now the bandwidth of the amplifier must cater to this shifted signal f1 plus b. So, now if this is the bandwidth of the signal, f1 plus b is the required bandwidth of the amplifier, and therefore, the amplifier now need to cater to this higher speed or faster signal, and hence its bandwidth must be so much high. And we know that if the bandwidth is supposed to be higher, we are going to have again constraints, conflicting constraint coming from the gain side. You have the thermal noise also, which is going to be impacted if you are trying to increase the bandwidth. So, larger chopping frequency necessitates higher bandwidth of this amplifier. Earlier it was operating in the baseband and the signal content was within 100 hertz. So, we would happy with even 100 hertz bandwidth, but now if I am operating with a few kilohertz of chopping frequency, the cutoff frequency of this amplifier has to be few kilohertz, and along with that you are going to have the constraint with the gain. So, you are increasing the bandwidth, the gain will be difficult to maintain. As a result, you will have to once again take care of the precision consideration, try to maintain the gain at the required value by looking at other trade offs like sizing, etc. So, for example, if you are trying to increase the cutoff frequency by say increasing the bias current, that will going to reduce your RO and hence increase the bandwidth of this circuit. At the same time, it is also going to reduce your open loop gain. Otherwise, likewise you have other scenarios as well, where you are having the compensation with the help of CC. There also you may need to relax the compensation capacitor value, and that is going to exchange or trade off with your phase margin. So, if we try to go for larger and larger chopping frequency, it has negative impact on the overall gain, open loop gain of this amplifier that you can achieve. And once again, you need to make sure that at this frequency, while satisfying the bandwidth requirement, it is able to meet your stability criteria, it is able to meet your phase margin. So, both of these are getting tightly coupled. The other issue that also needs to be taken care of is the optimization of the white noise and the 1 upon f noise together. So, the white noise can also be pushed down if you use appropriate sizing constraint. The white noise can also be pushed down further and further, so that your overall noise integrated over the signal bandwidth is lower. For example, after the anti-chopping operation, when you are pushing the signal back at this frequency, there once again the 1 upon f noise is not coming into picture, but the white noise indeed is coming into picture, and that is once again aligned with your signal content. Not only this, if you see after the anti-chopping process, you also have the higher harmonics of this clock signal coming at this point, right. So, you have not only f1, but the higher harmonics of f1 multiplying this 1 upon f noise spectrum. Therefore, this white noise that was present at all the higher frequencies, because it is continuous and it is going to be present at even higher frequencies. So, it is also going to have spectrum close to say 2 f1 and 3 f1 and so on. And now, when you are multiplying this 2 f1 component with this f1, definitely this the noise white noise component in this interval is also going to get shifted back and come to this level. As a result, you will have the white noise contribution piling up because of the higher harmonics of this chopping signal as well. Therefore, it is important to minimize the white noise component as well. It is not just the 1 upon f, but the white noise floor also needs to be minimized, so that when you are applying this anti-chopping process and bringing the white noise components associated or located close to this higher harmonics, say 2 f1, 3 f1, 4 f1 back to the lower frequency omega equal to 0, you are once again increasing the white noise floor close to the signal level, and that can start corrupting your data, and therefore, minimization of the white noise floor also becomes important. And for that, once again we have to look at the overall expression that we have for the white noise component, which is dependent upon the GM of the input device, W by L of the input device, and primarily if I look at the first two component, it is the bias current of the input device and the W of the input device that needs to be sized up. So, once again this constraint needs to be followed. You need to make sure that the white noise contribution coming from the first two sources, they are also sufficiently diminished, so that when you are applying the anti-chopping process, the overall level does not really go up and degrade the signal to noise ratio. In general, if you are having an overall low pass filtering operations, so that after a certain point the noise contributions are getting diminished. So, in that case the higher harmonics of these clock signals, which are anyway diminishing in amplitude. So, you have f1, 2 f1, 3 f1. So, these are the guys which are bringing my white noise back to the low frequency and superimposing on the DC. So, of course, as we go towards higher and higher harmonics, their amplitude also diminishes. So, it is a convergent series, it is not going to diverge, and apart from that you also have some low pass filtering effect in the circuit, which is going to diminish the components at higher frequencies. But still this series converging towards finite value over here, we need to minimize that finite value, so that we can maintain a good signal to noise ratio. So, that sizing constraint also needs to be taken care of. Now, this effect is termed as noise folding, where you are folding the high frequency white noise back to the base band, and which is now overlapping with your desired signal. So, this mandates lowering of white noise also to as low value as possible, and we have to take care of both these together, white noise as well as the 1 upon f noise. So, in some of the simulation examples also we will be looking at these sizing problems, how to co-optimize this combination. So, you have the choice of 1 upon f corner frequency, you have the choice of chopping frequency dependent upon that. The moment you go for higher chopping frequency, you have power dissipation increasing, bandwidth requirement increasing, and then you also have to make sure that the white noise spectrum is sufficiently low, so that when you are anti-chopping, it is not folding back sufficient noise. This folded back noise is also limited. So, all those constraints needs to be addressed while designing the chopping for mitigation of low frequency noise.
Sir, is clock signal is 0 to VDD or minus VDD by 2 to plus?
Clock signal can be just 0 to VDD. So, because here I have done the single ended versions, as I have discussed earlier also in some of the other examples, ultimately the signal is differential, and you can have switch which is applying the differential signal to the positive and negative terminals of the amplifier in turn. So, if I look at the phases, this will be the phase 1. During phase 1, the input signal V in plus and V in minus, they are coming to say V plus and V minus of the amplifier, and during the phase 2, which basically is these two switches, let me draw it phase 2 and this is also phase 2. So, during phase 2, these two switches are on. As a result, Vi plus goes to the negative input of the amplifier, Vi minus goes to the positive input of the amplifier, and effectively it is multiplying it by plus minus 1. So, that is the way plus minus 1 implementation is done. It is not that the clock signal has to be plus minus 1.
So, in that case, when you multiply with that signal, not only F1, F2, F3, it has some DC component also.
In this case, you do not have DC component because you are multiplying with plus minus 1. So, here the signal V plus and Vi minus, that is at one time it is applied directly to the plus and minus signal of the or plus and minus input of the amplifier. So, this entire Vi plus Vi minus appears over here plus minus, and in the phi 2 phase these cross switches are on in the phi 2 phase. So, Vi plus is connected here and Vi minus is connected here. As a result, it effectively means you are multiplying the signal by plus minus 1, because in one stage it will be multiplied by the gain. Suppose the gain is R2 by R1 or C2 by C1. So, in first phase phi 1 it is getting a gain of minus C2 by C1, in the other case signal is getting a gain of plus C2 by C1. So, effectively that is how you are multiplying it by plus minus 1.
So, why noise spectrum also shift means here the noise spectrum is multiplied and then it is multiplied, that means added to the signal and then it is come out at output node, but here you draw that after anti-chopping the noise spectrum come at F1. So, can you state this what is happening?
No, so the noise spectrum here to begin with, the 1 upon F noise was at lower frequency peaking at omega equal to 0, and then you multiplied with F1. This was the noise spectrum. At this point, you are getting the noise of the amplifier 1 upon F noise peaking at low frequency. When this gets multiplied by this chopping frequency, it goes towards the F1 and higher harmonics of F, and the signal frequency which was sitting at F1, it comes back.
Then after we apply low pass filter.
Low pass filter amplifier itself having its inbuilt low pass filter which will suppress. So, you may not need a dedicated low pass filter, but amplifier itself will have, or subsequent filtering stages anyway you will have additive aliasing filter. So, they will anyway have such a cutoff frequency, because only the amplifier's bandwidth is high, because you are processing the chopped signal which is at high frequency. The amplifier bandwidth is supposed to be high, but after that the low pass filter etc., anti-aliasing filter that we have, or the subsequent amplifier stage that you will have, even after that, as I said, you will need another amplifier stage which is probably going to be a variable gain amplifier whose gain need to be controlled in automated fashion. So, that itself will not require chopping and its bandwidth will be much lower. So, or low pass filtering will be inbuilt in the circuit stages subsequent to this also, and beyond that you anyway have the low pass filter. Okay, so we can close our discussion here, and in the next section possibly we are going to look into some other examples where the noise constraints will be different. We will see that in the folded cascode example also we will be looking at the noise analysis, frequency analysis, stability analysis, and how it is very different from this case. Now we have the steps for arriving at sizing. So, now given a specification, higher level specification of the amplifier that we have started with in the beginning, using all this information of noise analysis, frequency analysis, stability, gain requirement, bandwidth requirement, using all this analysis, we can arrive at transistor level design. We can estimate what should be the required transistor designs or transistor sizes for a front end amplifier. Some of the things that we have already studied in our earlier courses is the signal swing, the input common mode range, the overall output common mode range. So, they also act like important parameters. So, combining what we have studied like the noise and the stability along with the other parameters that come in like the input and output signal range and some other important issues like CMRR, PSRR that we have not dealt with so far. All these so many issues combined together help us determining the sizing required for the transistors. So, some some features or some specifications may be important, some other specifications may not be important. Like if I am talking about the front end amplifier, their input common mode range will not be very important, or input signal range will not be very important, because the input signal is very small in quantity. Likewise, there is an important quantity called slew rate for the amplifier, which deals with large signal operation at the output stage. If the input signal is changing fast and by a larger magnitude, the amplifier slews, and the output state transitions are determined by the bias current and the load capacitance. So, slew rate happens when the input signal is changing fast and getting amplified by large amounts, so that the output has to swing very fast. One of the input devices becomes completely off and the other one becomes completely on. So, that is the extreme case of the differential amplifier. The slew rate also appears as one of the important specifications for the amplifier or the op amp. So, for the front end amplifier, once again slew rate may not be so critical, because the front end amplifier, the very first stage is not introducing so much of slew, because the voltage amplified after the first stage is also pretty small in magnitude. So, at the max you are having few hundreds of gain, and the input magnitude is 10 microvolt. So, you are still within maybe few millivolts after the first stage. So, you may not so much worry about the slew rate of the first stage amplifier also, whereas noise constraint becomes very important for the first stage. So, noise is going to play a heavy role in determining the sizing of the transistors, the W by L of the transistor, bias current of the transistor. Likewise, the chopping constraint and the bandwidth is going to be very critical for the first stage amplifier. For the subsequent stage, like the variable gain amplifier, which is taking the amplified signal, the noise constraint will be relatively relaxed. You may not be employing chopping over there, so bandwidth constraint will be relaxed, but it will be amplifying the signal to a large magnitude, and therefore, the slew rate and the output signal swing can be important. Input signal swing may not be so critical. If you go deeper into the chain, the filter, they are receiving a fully processed or magnified signal, which is at least maybe a few tens of millivolt, 100 millivolt, and therefore, there the input signal range will also become very critical. So, depending on where you are in the stage, noise or swing, one of these two will be more critical. Likewise, the other parameters like the input signal range and output common mode range, the bandwidth of the circuit, and some other specification like CMRR, PSRR, they will also become important. So, as you are in the earlier stage of the circuit, as we said that the CMRR and PSRR, they are going to be very crucial, because even a small mismatch between the transistor pair can lead to propagation of any noise in the supply to the differential signal. So, any common mode noise which is appearing from the VDD or the ground sources, they can completely overwhelm your differential signal that you are having at the output. So, these are other important specifications that we may need to take care of. So, we can see that there are so many specifications, and based on those we need to arrive at the transistor sizing and block level implementations while meeting our target specs at different blocks or different stages in our whole signal processing chain. And whatever we do here, whatever baseline analysis we do here, applies to any other general application or any other architecture that we are building. So, here we are discussing a baseline design, going down from the highest level specification down to all the different kinds of analysis, and finally arriving at the bottom line transistor level design. And whatever we do here applies in a similar fashion to other topologies. The concepts remain very much similar. So, probably we will take another parallel example where some other amplifier topologies will be taken up, and the similar concept will be applied to show you another variation, another taste of similar analysis or similar approaches, so that you are comfortable with applying the similar strategy for any other design that you may take up.